All right, everyone. I am here with Melanie Mitchell. Melanie is the Davis Professor of Complexity at the Santa Fe Institute, as well as a professor at Portland State University and author of Artificial Intelligence, A Guide for Thinking Humans. Melanie, welcome to the TWiML AI podcast.
Thanks for having me. Happy to be here.
Thanks for being on. I'm super excited to jump into our discussion. Why don't we start by having you share a little bit about your background and how you came to work in AI?
So I was a mathematics major in college. I didn't really know what I wanted to do, but I happened to read Douglas Hofstadter's book, Gödel, Escher, Bach, An Eternal Golden Braid, which, like many people of my generation who read that, really was the push to get me to get into the field of AI. But nice. I not only did that, but I also sought out Douglas Hofstadter and convinced him to take me on as a graduate student in computer science, even though I'd never taken a computer science course before I went to graduate school. So I went to University of Michigan, got my PhD there, working with Hofstadter, but also with John Holland, who was there at the time and is the pioneer of genetic algorithms and the field that's now called evolutionary computation. So I got a lot of sort of non-mainstream training in computer science and artificial intelligence, cognitive science, and that's really shaped my own research in this whole area.
Nice. Tell us about your research. You have mentioned your professorship in complexity, which is a topic that I'm looking forward to digging into with you. But kind of give us the lay of the land of your research interests.
Right. So I've done research in a lot of different fields, ranging from modeling how people make analogies and trying to get AI systems to make analogies. I've also worked in genetic algorithms and the whole field of sort of evolutionary AI, evolutionary machine learning, and complex systems. So what is complex systems? It's very broad umbrella, kind of like AI, where people are trying to understand how relatively simple collections of relatively simple systems can produce complex emergent behavior. And one of the sort of canonical examples is we have hundreds of billions of neurons in the brain. Each individual neuron is relatively simple compared to the whole collective, and yet we get these emergent properties like that we call intelligence, cognition, consciousness, etc. So people in complex systems are trying to study that kind of emergent phenomenon across disciplines. But there's a lot of interest in intelligence as a natural phenomenon that's not just in, say, humans or even animals, but also in collectives like culture or economies or other kinds of, large social insects, things like that. So the question, what is intelligence and how can it manifest itself, is really a primary focus of complex systems. And in that sense, it overlaps with AI, which is itself struggling with the question of what is intelligence and what does it mean to be intelligent.
And so as a researcher thinking about these challenges from the perspective of complex systems, how do you go about that, or what are the big questions that you're asking that push artificial intelligence forward?
So intelligence is one of those terms that has been used in so many ways, is so confusing. And yet it's the central term of our field, AI, right? I think John McCarthy, who coined that term, artificial intelligence, later regretted it because, for one thing, he didn't want it to be artificial. He wanted there to be intelligence, but also because intelligence itself is such a ill understood phenomenon. So one of the things that we're doing at the Santa Fe Institute during my leave as a professor there is to bring together people from different disciplines to talk about intelligence. And that involves the usual disciplines like AI, neuroscience, psychology, but also people from the world of other kinds of biological intelligences like social insects, or we even are talking about the intelligence of things like the immune system, which is a very key topic these days. We're struggling with this pandemic. And trying to get insights for what people mean in different disciplines by this term, and how these different notions could inform AI. I mean, one example that I'm particularly interested in is the notion of social intelligence. There's people who would say that there is no intelligence without social relationships, that intelligence, in fact, evolved because of the sociality of primates, for example. And yet in AI, we kind of study intelligence as in the sort of brain in a vat metaphor, where there's this individual agent, or this individual computer that's trying to learn or produce intelligent behavior without any sort of social interaction.
Yeah.
So how can that even be intelligence? So that's one of the questions that we're looking at.
It's interesting to think of it in that context. You could argue that even the act of labeling data is a social interaction relative to the intelligence.
It's a very weird kind of social interaction, I guess, because it's one in which there's one active party, namely the human, labeling the data, and there's this passive perceiver who's trying to learn from what the human's labeling is. That's very unlike the way that, say, children learn or any other animals, where learning is much more an active process. It's not a supervised process largely. It's an unsupervised process. So I think a lot of people in AI are sort of realizing that passive, supervised paradigm for learning is quite limited. And now there's much more focus on unsupervised, or so-called self-supervised, and active learning that's in some ways inspired by the way that children learn.
Are there examples that you cite of kind of social learning and how it, does or could play out in an AI context?
Well, this is, I mean, there's some people who are trying to build models of this kind of social learning, like imitation. That's another form of learning that's not sort of passive. It's more active. It's like, I look at you, I try and do what you did. But that comes back to the question of analogy, because whenever I'm trying to imitate something, to do what you did, I'm actually making an analogy and trying to map that onto my own myself, looking at something very different that you did. So this was part of what my research in analogy was trying to get at, was to understand sort of this essential similarity between what somebody else does and then how I can do that in my own way, to learn in that way. So I think that's a key way that people learn, is by analogy.
And so in that research thread, how do you frame the problem, or what's the setting for that you created the paper around?
Right. So my PhD work with Douglas Hofstadter was on getting computers to make analogies in an idealized domain, sort of micro world. And our micro world was strings of letters. Now, the goal wasn't to get a program that could make string analogies, but rather to capture something about real world analogies in this idealized domain. And so we had analogy problems like, if the string ABC changes to the string ABD, what does the string IIJJKK change to?
Mm-hmm.
So that's kind of an imitation, right? It's an imitation kind of task. But the problem is that I can't imitate it literally because, you have a different situation, a string of letters in which maybe there's groups of letters instead of individual letters. And this sounds really trivial almost, these letter strings. And yet we created thousands and thousands of these analogy problems in that capture all kinds of very subtle concepts.
Mm-hmm.
And it's actually very challenging. And I wrote a program that could do some of these analogies. Other people have tried other kinds of approaches, but nobody's been able to solve even these simple seeming problems with the same generality that humans can.
Mm-hmm.
And I think, the other people have invented other kinds of idealized domains for analogy. One really popular one in the machine learning community right now is the Ravens progressive matrices, which are kind of an IQ test that are used on humans, but people are now looking at how to solve these problems using machines because they capture a lot about analogy and abstraction. There's a whole bunch of different interesting idealized domains. And what's kind of paradoxical is that while we have these machines that can do incredible things, like they can recognize faces, they can translate between languages, they can generate very human-sounding text, and yet they can't do these very seemingly simple abstraction and analogy problems that are so easy for humans.
Mm-hmm.
So it's something that we're definitely missing in the field.
It kind of calls back into question this fundamental definition of intelligence, and are these models really learning, or are they memorizing? What is their ability to reason, that kind of thing.
Exactly. And in any definition of intelligence, I think the idea that we can take what we have learned and use it in new situations is absolutely central. In machine learning, people call that transfer learning, or generalization, mm-hmm. out of sample generalization, or things like that. But it really is an issue of being able to abstract, to make the right kind of conceptual abstraction, and to make analogies. And that's something, the lack of that has actually caused some of the lack of robustness in the systems we have today. People talk about self-driving cars, and self-driving cars are really good, except if they encounter some situation that's way outside their training distribution. So how do we humans deal with those kinds of situations? Well, we use prior experience and kind of common sense, where common sense is being able to apply our prior experience to our new situation. And that's exactly what analogy is.
Mm-hmm. Mm-hmm. Did your research in this area propose or uncover frameworks or ways to help machines work with analogies?
So I recently wrote a kind of review paper that tried to survey some of the different ways that people have approached this problem of analogy. And there's several different approaches. So one approach that goes way back is sort of symbolic, good old-fashioned AI approach, which translates situations into predicate logic statements, and then tries to make mappings between predicate logic statements using rules. It's kind of a rule-based system. So that's one approach. The polar opposite of that might be the sort of deep learning approach, which people have applied, where you have some kind of deep learning system that is trained on tens of thousands of examples of these analogies and then tries to solve new ones. Okay, and each of these have a rather different set of limitations. The sort of symbolic AI systems don't learn. They don't learn in any kind of very robust way. a lot has to be built in by the programmer.
Mm-hmm.
They tend to be somewhat brittle, hard to scale. The deep learning systems have their own problems, which is that they have to be trained on extensive sets of training data, which is very unhuman-like. And I mean, the whole purpose of analogy is that it's meant to be a few-shot learning process.
Mm-hmm.
And so it doesn't really make sense to have to train on lots and lots of analogies in order to do new analogies. And the other problem is that these systems are often very opaque. It's hard to know what exactly they learned. And in many cases, they've been shown to have learned sort of spurious correlations that aren't really, so they're not really doing the task we wanted them to do. They're using shortcuts. Mm-hmm. My own work with Hofstadter was on a different kind of system that was more cognitively inspired. It's more like a cognitive architecture that has a sort of working memory, a long-term memory, perceptual processes that unfold over time. And it's reminiscent of what people used to call blackboard systems, where a working memory is kind of a blackboard for agents that try and post their hypotheses on this blackboard and try and communicate with each other and also compete with each other. So, but it also had some limitations. You know, it didn't do learning. It was a little bit more on the symbolic side. It still remains to be seen that it's going to generalize. Now, the most recent kind of approach that people have used is what's called the probabilistic program induction, which the idea now is that a concept or an analogy is represented in terms of a program in some particular domain-specific programming language that's defined by a kind of grammar. So you can generate programs from this grammar, and you can do it probabilistically based on sort of the data that is given to you, and you search for a program that can generate the correct answer. So there's a lot of work in this area. It's really interesting. Some people have combined it with deep neural networks, and I find it very promising. But its big problem is that it's extremely computationally expensive. It requires a huge amount of search. And also, it does require humans to build in quite a bit of prior knowledge. So in my paper, I kind of said, okay, here's all these different kinds of systems and all these different domains that people are working in. How do we make progress? How do we sort of bring all this together and really figure out a way to assess how all these systems are performing and what they're all lacking? You know, we need some kind of common framework for evaluating all of these different kinds of systems, which we don't yet have.
Yeah. You mentioned that you came up with in your early work in this kind of letter game. Are there other established benchmarks or problems for analogy?
Yes. So there's sort of two groups, I would say. There's this linguistic-based analogies. So this became more popular recently with word embeddings. People showed that you were able to make a sort of single-word analogies via word embeddings, like man is to woman as king is to blank, right? Mm-hmm. And that was sort of work, didn't always work. But people have tried to look further at that kind of thing. And then there's the more idealized non-linguistic analogies, like our letter string examples, like the so-called ravens, progressive matrices. There's another newer set that's been proposed by Francois Chollet of Google called the abstraction and reasoning corpus, which is a set of analogy problems that are sort of idealized visual problems that try and capture what psychologists call core knowledge, things that they think are innate in humans from birth, say, like the notion of objects and object interactions and some other basic spatial temporal knowledge. And Cholet came up with something like 1,000 of these problems. He released 400 of them, put this as a challenge on the Kaggle website.
Mm-hmm.
A lot of people competed. There was 600 hidden problems, and they were few shot learning problems. So it would give like 3 examples and now a new problem, okay, which was a analogy. Do the same thing as the examples, except now with this new visual input.
Yeah.
And no one was able to solve this in any general way. And it's a lot of people now really are looking at what's missing from our current systems that we need to do this kind of abstract reasoning. He called it the abstract reasoning corpus.
Mm-hmm.
And it was part of a paper he wrote called On the Measure of Intelligence, which was about how do we compare AI systems with humans in a fair way.
Yeah. Are there, do you see the, just trying to connect our couple of conversations so far, do you see this social learning idea or complexity theory as contributing to being able to solve these types of problems? Are there examples of, some type of social solution being a better approach to helping a machine figure out analogy?
Yeah, that's a great question. And I don't really know the answer. I mean, I think that, being able to do this kind of imitation, this kind of analogical imitation is key to our social interactions. So maybe that's kind of the opposite. So analogy helps us with social interactions. I have a kind of, I can map, say, my own actions to your actions or my own mind to your mind. I have a theory of mind, and all of that requires a kind of analogy, analogical thinking. I think our analogical abilities arose in part because of the pressures of our social interactions, whether some kind of modeling of social collective behavior is useful for making analogies. I'm not quite sure how to frame that question, but I want to think about it more.
What do you think? What does all this tell you about kind of where AI is? Like, how do you kind of frame the progress we've made in AI from kind of the early days of symbolic to deep learning now, given, that we struggle with, basic analogies and there's no concept of social learning or limited, concept.
Yeah. So that was kind of the impetus for writing my book. I was confused about where the state of AI was. You get all these people who are saying things like, AGI is going to be within the next 10 to 15 years. There are polls where they polled AI, researchers. How soon do you think we're going to have human level intelligence? And everybody always, a lot of people in AI say, yes, I think within a few decades, we'll get there. And that's been, of course, going on since the beginning of the field. And so a lot of those predictions turned out to be wrong. But then you get other people saying, really, we've made no progress. There's no progress towards general AI. There's only progress in narrow domains. So I tried to write this book. I tried to figure out what was going on. Where are we? And, what I find is that indeed AI has made great progress in a lot of what we might call narrow domains, like speech recognition, translation, all of these things. But even in those domains, it has some brittleness still. It has brittleness in, say, object recognition. It makes unhuman-like errors, and it's vulnerable to these adversarial examples, which are very unhuman-like. Mm-hmm. And why is it brittle? I mean, what causes this brittleness? Well, I think it's the lack of this ability to do abstraction and analogy. That's really a big part of it. It's that in psychology, there's this distinction between so-called perceptual categories and concepts. So you can think of something that's learned from, say, the ImageNet data set, how to recognize, say, a bridge. That's a perceptual category. It's using perceptual features to discriminate among categories. But we humans have a much richer notion of bridge, something that's what I would call concept, where we can extend it, we can abstract it. I can say, I want to bridge the gender gap, or I want to, I wrote a bridge to the song, or, we use these terms in very abstract ways that makes us, I think, more robust in our recognition and understanding of the world than these AI systems. So I want to figure out a way to give AI systems concepts as opposed to perceptual categories.
Mm-hmm.
Now, Hofstadter had a great quote where he said, a concept is a package of analogies. And that, with the example of bridge, you can really see that. Because when I say, like Joe Biden, when was running for president, he said, I'm a bridge to future generations. And that's really an analogy. He's making an analogy between the regular perceptual notion of bridge and the more abstract notion of bridge. And that's how we build our concepts and make them rich and robust.
And so do you think we get there with current approaches to AI? Or do you think we will require some totally different set of approaches currently existing or otherwise?
Yeah, I think that's an unknown question. My own opinion, and it's an opinion, is that there's kind of a missing link that we haven't discovered yet. There's a missing set of approaches. Now, other people, like I saw Jan LeCun recently, was promoting sort of self-supervised learning with transformer networks and saying, this is the way AI is going to become general. It's going to sort of watch videos all day and learn like a baby. I think that was his quote, which is, of course, not how babies learn at all. But that view that if we just use the current systems we have and make them bigger, train them with more and more data, then we'll somehow magically cross this barrier where machines will suddenly now become like humans. I don't think that's going to happen with the current set of, the current repertoire of architectures that we have today. I think there's something very deep missing, and I think that we can learn a lot by looking at other kinds of intelligences that appear in nature, biology, and otherwise, to inspire us.
Mm-hmm. One of the things I noticed in reading the blurbs about the book is you reference AI is terrifying, or not necessarily that. That's my question: does AI scare you? Do you think AI is terrifying? Terrifying is used several times in the description of the book, and who knows if that's the publisher or Melanie.
Right. No, actually, that word came from Hofstadter, my former PhD advisor, who I talk about in the book, how he was invited to go give a talk at Google to a bunch of AI researchers at Google, and they were all, I came along to this talk, and they were all like me. They had got into AI because they read Hofstadter's Gerd Lescherbach. They're super excited to see him talk, and yet what he said was, I'm terrified about AI. Mm-hmm. And his terror was that you know, he sees intelligence as this very profound, complex process that should be hard to get to. And yet he's worried that there will be these, what he called cheap tricks that will enable us to get to intelligence in this way that kind of cheapens its profundity. And a cheap trick might be, you know, sort of like
A
a language
transformer
model.
with
Yeah, transformer, right, exactly. So I was trying to understand this, you know, that didn't terrify me.
uh-huh.
I'm more terrified of people using AI in ways that it's not ready to be used in some autonomous way.
Mhm.
You know, that trusting it too much, as we've done, you know, like governments have done with face recognition. They've said, oh, we can now apply this to law enforcement and surveillance, and we've seen that these facial recognition systems can make terrible errors that really affect people's lives and have biases that are present in the data that they're trained in and other factors that can really impact people's civil rights, say. So that's more of the kind of thing that terrifies me, that AI is going to be used in a way that it's not quite intelligent enough to be used in.
Mm-hmm. Well, we certainly already see plenty of that. Is analogy a solution to that potentially, or potential contributor to that? In a lot of ways, kind of our human, you know, biases and you know, those come from analogies that we make, right?
Sure.
And that we inappropriately apply, you know, across, you know, race, gender, you know, all kinds of things, right? So does figuring out analogy help us get to a better place, or enable, you know, the thing that you fear?
Yeah, that's a wonderful question. And yes, stereotypes are analogies. Now, I think there's an open question that, can we get to human-like intelligence in machines without incorporating human-like prejudices?
Mm-hmm.
I would say the answer is no, we can't. I don't think we can separate them. It's a worry, you know. I do think that humans also have, you know, they have lots of biases and prejudices, and some of them come from analogy. But we can't take analogy out and still have intelligence.
Mm-hmm.
So it's kind of like a side effect, a
Mm-hmm.
negative side effect that we humans have to work ourselves against in avoiding, you know, biases and prejudices and so on. Can we get an AI that's as intelligent as us but doesn't have these kind of negative side effects? I don't know, but I would guess no.
Mm-hmm.
And, you know, this question comes up all the time. Can we separate intelligence, sort of pure intelligence, if you will, from other kinds of things that go along with say, human intelligence? So, like, I know Stuart Russell wrote this book called Human Compatible, in which he has all of these scenarios where you have a super intelligent robot, let's say, that figures out how to solve climate change by killing all the humans.
Mm-hmm.
Okay, no more carbon emissions. But it's like that assumes that you can separate sort of reasoning from common sense. And I don't believe those things are easily separable or even possible to separate. But I think we're arguing about that because we don't really understand intelligence. So that gets back to this question of,
Mm-hmm.
you know, is intelligence in some sense orthogonal to common sense? Is it orthogonal to biases? Can we have a machine that's like has the best of us but not the worst of us? I don't know. I don't think so.
Mm-hmm. Yeah, and maybe to close out, what are the things that you think? Are there things that you're excited about, or that you think that we should be doing more of to really help us understand this core of what is intelligence?
Yeah, I mean, I see more and more interaction between AI people and neuroscience people and cognitive science people, and a lot more focus on of machine learning people on child development. People are looking at how babies learn. You know, DARPA has this Foundations of Machine Common Sense program now, where people are trying to build machines that can learn and kind of go through the same developmental stages that babies do. It's interesting. We'll see what happens there. People are putting GoPro cameras on babies' foreheads and getting new data sets for training machines to do visual recognition by getting the kinds of active views that babies try, that the way that babies observe the world. And it turns out that those views tend to produce data that's more robust, that machines become more robust when they train that way. So I really think that interdisciplinary thinking and research is really important. And it's really the way the field started. AI started as an interdisciplinary melding of psychology, philosophy, neuroscience, et cetera. It's kind of pushed away from that in a way because it's become so commercially successful. So it became more about engineering than about science. But I think now that the engineering has kind of gotten to a certain point and people are realizing that there's limitations, that people are now returning to this more the sort of science phase of AI, where now we have to really understand more about intelligence. So I think that's very positive.
Yeah. Awesome. Well, Melanie, thanks so much for joining us. It's great to learn a little bit about your research, and I'm super excited about this idea of the intersection between complexity and AI. I think a lot of fascinating stuff to come there, hopefully.
I hope so too. Thank you very much.
Awesome. Thank you.